Welcome to Fluent Daily, the English listening channel for advanced learners at B2 and C1 level. Every episode features a rich, flowing conversation in natural English on a topic that is genuinely worth thinking about: history, psychology, science, philosophy, and more. There are no simplified sentences here, no slow speech, no vocabulary drills. Just real English spoken naturally on ideas that matter. This is Fluent Daily. Let's get into it.
Today we have a great story, so let's get started right now.
Right now, like literally right as you are listening to this, there's a massive war going on.
Oh, absolutely.
And I don't mean somewhere across the globe or, in some abstract political sense.
Okay.
I mean literally right this exact second, inside of you.
Right, inside your own body.
Exactly. And it is happening at a scale that is just, it's completely mind-boggling. We are talking about a biological intelligence that is tasked with protecting roughly 37 trillion cells.
Give or take a few billion, yeah.
Right, give or take. And it is constantly surveying the landscape for something like 10,000 different types of foreign molecules.
At least.
At least. And it is doing all of this using an active standing army of approximately 2 trillion immune cells.
It's a staggering logistical operation. I mean, just the sheer math of it is hard to wrap your head around.
It really is.
2 trillion cells constantly moving, communicating, and basically making life or death decisions entirely invisible to us.
Right.
We operate completely without conscious awareness of it. Well, until something goes wrong.
Yeah, we just go about our day drinking coffee, answering emails, complaining about traffic, while 2 trillion of our cells are basically running global security for our body.
That is a great way to put it.
And that is the mission of today's deep dive. We are unpacking the architecture of the human immune system.
Yes, we are.
We're going to explore this incredibly sophisticated distributed network that has basically evolved over hundreds of millions of years, right? In a constant, relentless arms race against pathogens.
A literal arms race, yes.
So we'll look at the historical discoveries, the cutting-edge clinical data, and the raw biology of how this system actually works.
And, the timing for this deep dive couldn't be better. I mean, the COVID-19 pandemic threw immunology right into the global spotlight.
Oh, totally. Suddenly everyone knew what an antibody was.
Right. It forced everyone to pay attention to concepts that, they used to be confined to medical textbooks.
Yeah, household words now.
Exactly. And scientifically, that period accelerated some massive breakthroughs. I mean, we saw the validation of mRNA vaccine platforms on a global scale.
Which we will definitely get into later because that is wild.
It really is. And we gained a much deeper understanding of how our T cells respond to novel threats. But we also saw the terrifying reality of immune dysregulation.
Right, like when the system backfires.
Exactly. Conditions like long COVID really exposed what happens when this incredibly powerful system loses its calibration.
Well, I want to start by challenging the very phrase we use to describe it. Because when we say the immune system, I immediately picture like a single unified thing.
Sure, like an organ.
Yeah, like the heart. It's a pump, it sits in your chest, it has tubes going in and out, and it does a specific job.
Right.
But looking at the scope of this, calling it a system, feels, misleading. To me, it feels less like an organ and much more like a decentralized intelligence agency.
Oh, I like that.
You've got operatives, you've got surveillance cameras, and weapons manufacturers scattered across the entire globe, operating in different time zones with wildly different protocols.
That intelligence agency framework is actually a much more accurate way to model it.
Really?
Oh, absolutely. It is absolutely not a single organ. It is a highly distributed network spanning your entire physiology.
Perhaps.
You have distinct cells, tissues like the thymus and spleen, lymphatic vessels, and these incredibly complex chemical communication signals operating everywhere at once.
Well, it's everywhere.
Everywhere. And its functional architecture only really makes sense when you look at it through the lens of evolutionary history.
What do you mean by that?
Well, the immune system is essentially a living archaeological record of every threat our ancestors ever faced.
Oh, wow.
Yeah, every time a pathogen developed a new way to evade our defenses, our bodies had to develop a countermeasure.
So it's reactive.
Exactly. And every new adaptation on our end forced pathogens to find new loopholes.
The ultimate cat and mouse game, played out over hundreds of millions of years.
Precisely.
But to understand how this massive intelligence agency actually functions day to day, we have to look at its two distinct evolutionary strategies.
Right, the two main branches.
Yeah, the literature breaks this down into a fundamental trade-off between speed and precision.
And that division is the core organizational principle of immunology. You have innate immunity on one side and adaptive immunity on the other.
Okay, let's start with innate immunity, since that's the first line of defense, right?
First line is exactly the right way to think about it. The innate system is ancient.
Like how ancient?
Evolutionarily speaking, we share elements of it with fruit flies and even plants.
Wait, plants have an immune system?
They have innate immune responses, yes. And its primary defining characteristic is sheer speed.
Oh, fast.
Very fast. It activates within minutes, sometimes hours, of encountering a pathogen.
Wow.
But the biological trade-off for that speed is that it is entirely non-specific.
Non-specific meaning what? It just attacks anything.
Pretty much. It is a blunt, highly metabolically expensive instrument. Its main job isn't necessarily to eradicate the disease entirely, but just to contain the threat early before it can, spiral out of control and kill the host.
So when you say blunt instrument, I immediately picture cells fighting.
Yeah.
But the innate system isn't just the soldiers, right? It's the actual walls of the fortress.
Yes, exactly. The very first layer of innate immunity is purely physical and chemical barriers. We often take them for granted.
Like our skin.
Right. Your skin is a massive, multi-layered physical barrier that is incredibly hostile to microbial life.
Hostile. I mean, it just feels like skin.
To us, sure. But to a bacteria, it's a desert, it's dry, it's slightly acidic, and it's constantly shedding outer layers to physically remove attached microbes.
Oh, so they just fall off with the dead skin cells.
Exactly. Then you have mucous membranes lining your respiratory and gastrointestinal tracts, which literally trap invaders in a sticky web.
Gross, but effective. And there's an active mechanical component to that too, right? I was reading about ciliated epithelium.
Yes, those are fascinating. Ciliated epithelium refers to these tiny, microscopic, hair-like structures lining your airways.
Okay.
And they beat in a synchronized upward rhythm.
Just microscopic brooms constantly sweeping mucus and trash up and out of your lungs so you can cough it out or swallow it.
That continuous escalator is vital. If those cilia stop working, which, by the way, happens in certain genetic conditions or even temporarily from smoking respiratory infections, just skyrocket.
Wow, just from the brooms stopping.
Yeah. And then you have the chemical warfare side of these barriers.
Chemical warfare.
Oh, yeah. Your skin produces antimicrobial peptides. Your stomach maintains a highly acidic environment, a pH of around 1.5 to 3.5.
Which is basically battery acid.
Pretty close. And that denatures and destroys the vast majority of pathogens you ingest with your food.
Okay, so skin, stomach acid. What about things like tears and saliva?
They contain powerful enzymes like lysozyme.
Lysozyme.
Yeah, lysozyme literally cleaves the chemical bonds in bacterial cell walls, causing the bacteria to burst open.
Yeah, wait.
It's true. You are actively deploying antibacterial chemical weapons every time you blink or swallow.
It's wild to think that just crying or digesting lunch is part of this global defense network.
It absolutely is.
But, barriers fail. Let's say I'm working in the yard, I get a nasty scratch from a rusty nail, and bacteria breach the skin barrier.
Okay, the wall is down.
Right, the wall is down. Who are the ground troops that actually show up to the breach?
That's when the cellular defenders of the innate system step in. You have a whole roster of specialized cells, macrophages, neutrophils, dendritic cells, and natural killer cells.
Okay, I know macrophages. The name translates to big eaters.
You got it. Macro for big, phage for eater, and that's a literal description of their function.
They just eat things.
They do. They are stationed in tissues all over your body, constantly patrolling. When they encounter foreign debris or bacteria, they undergo phagocytosis.
Phagocytosis.
Right. They stretch their cell membrane around the target, engulf it entirely, and digest it using highly reactive acids and enzymes contained in internal compartments.
Just swallows it whole. But wait, how do they know what to eat?
That's the big question.
Because if the innate system is non-specific and ancient, it obviously doesn't have a database of the exact strain of bacteria on that rusty nail. If it's a blunt instrument, how does the macrophage know the difference between a piece of rust, a harmful bacteria, and just, one of my own skin cells?
That is the crucial mechanistic question. They rely on sensors called pattern recognition receptors, or PRRs.
Or PR.
Yes. They don't look for specific species of bacteria. Instead, they look for broad molecular motifs that are fundamentally characteristic of pathogens, but are never produced by human biology.
Oh, interesting.
We call these motifs pathogen-associated molecular patterns, or PMPs.
Okay, give me an example of a PMP. What does the macrophagous sensor actually bump into?
The classic example is lipopolysaccharide, or LPS.
LP.
Right. It is a major component of the outer membrane of certain types of bacteria. Human cells do not make LPS. We have never made LPS.
Okay, so it's a clear red flag.
Exactly. So if a macrophage's pattern recognition receptor bumps into a molecule of LPS, it doesn't need to know if it's E. coli or salmonella. It just knows this is non-self. This is a structural component of an enemy.
Right. It doesn't care about the ID card. It just sees a weapon.
Exactly. Another example would be double-stranded RNA floating freely in a tissue.
Why is that bad?
Because human cells keep their RNA single-stranded and safely inside the cell. Many viruses, however, use double-stranded RNA. If a sensor detects that, it instantly sounds the alarm.
Okay, so it bumps into this molecular red flag, it sounds the alarm, and then what? What is the actual result that I, the person with scratched arm, experience?
You experience inflammation.
Oh, okay.
When those receptors bind to a threat, the macrophage doesn't just eat the bacteria, it starts releasing chemical alarm signals called cytokines and chemokines.
Cytokines.
Yes. These chemicals act on the local blood vessels, causing vasodilation. The vessels widen, increasing blood flow. They also cause vascular permeability, meaning the walls of the blood vessels get slightly leaky.
Which is why the scratch gets red, hot, and swollen.
Yes. The redness and heat are from the increased blood flow, and the swelling is fluid leaking from the blood vessels into the tissue.
So it's doing that on purpose.
Absolutely. This leakiness is deliberate. It allows a massive influx of other immune cells, like neutrophils.
What are neutrophils?
They're basically biological suicide bombers.
Whoa.
Yeah, they show up in swarms, release toxic granules to kill everything in the area, and then they just die.
That is, wow.
And the accumulation of dead neutrophils and debris is what we call pus.
Okay, that is so incredibly metal and gross.
Yeah.
But mostly metal.
It really is.
And what about fever? Does the innate system cause that too?
It does. Some of those cytokine alarm signals travel through the blood to the hypothalamus in your brain, which is your body's thermostat. The cytokines essentially hack the thermostat and raise your core body temperature.
See, I always thought the fever was a side effect of the virus breaking things, like the engine overheating because it's broken.
Not at all. It is a highly coordinated defensive strategy. Many human pathogens have evolved to replicate optimally at 98.6 degrees Fahrenheit.
Our normal body temperature.
Right. By raising the core temperature, your innate system creates a hostile environment that physically slows down the pathogen's replication rate.
So it's burning them out.
Yes. And furthermore, the heat actually accelerates the metabolic rate of your own immune cells, making them fight faster and more efficiently.
So the fever's good for us and bad for them.
Exactly. You also experience a systemic acute phase response, where the liver starts pumping out proteins that bind to pathogens, and your body actively hides iron.
Hides iron? Why?
Because bacteria need iron to replicate, so your body just locks it away.
Man, it's a scorched earth tactic.
It really is.
It explains why you feel so incredibly tired and achy when you're getting sick. It's not necessarily the virus making your muscles ache. It's your own innate immune system throwing every single metabolic resource it has at the problem and deliberately making you want to lie down so it can use your energy to fight.
That's spot on. It's exhausting and it causes collateral damage to your own tissues, but it is remarkably effective at keeping infections in check during those crucial first few days.
Which brings us to the second evolutionary strategy. If the innate system is the blunt, fast, scorched earth instrument, the adaptive immune system is the precision arsenal.
The adaptive immune system is an evolutionary marvel, and it's found only in vertebrates.
Okay.
It operates on a totally different timescale. Where the innate system reacts in minutes, the adaptive system takes days, sometimes up to 2 weeks, to fully mount a primary response.
2 weeks is a long time when you have a virus replicating inside you.
It is, but what it lacks in speed, it makes up for with a level of precision and specificity that is frankly breathtaking.
All right, this is where we get into the math, and I need you to walk me through this slowly because it legitimately broke my brain when I was reading the source notes.
It is a lot to take in. So the central problem the adaptive immune system has to solve is anticipation.
Anticipation.
Right. There are millions of potential pathogens out there, and they are constantly mutating. How can your body possibly possess the genetic instructions to build specific weapons against molecular shapes that it has never encountered before?
Right, because if I understand genetics, every protein we make requires a specific gene. But we don't have millions of genes for millions of weapons. We only have about, 20,000 protein coding genes in our entire genome?
Exactly. 20,000 genes to build a whole human. We simply do not have the storage capacity in our DNA to hard code a specific receptor for every possible threat.
It physically wouldn't fit.
Right. So evolution found a loophole. It's a mechanism called VDJ somatic recombination.
Okay, unpack that. What is actually happening?
Instead of having a single gene for a single receptor, your immune cells have a localized cluster of genetic fragments. You have a set of V segments, a set of D segments, and a set of J segments.
Kind of like a menu.
Yes, like a menu. As a new adaptive immune cell develops, it performs a highly controlled random genetic shuffling. It randomly selects one V, one D, and one J segment, cuts the DNA, and splices them together to form a brand new, unique gene.
Okay, so mixing and matching.
But it goes further. During the splicing process, the enzymes deliberately make sloppy cuts.
Sloppy cuts on purpose.
On purpose. They add or remove random genetic letters at the junctions just to introduce even more chaos and variety.
So it's not just dealing a random hand from a deck of cards. It's tearing the cards in half and taping them back together randomly.
That's a great way to visualize it. And through this random shuffling and splicing, your body can generate an astronomical number of different, highly specific antigen receptors.
Okay, give me the number.
The math suggests the human body can generate up to 1 quintillion different receptor variations.
I want to make sure I'm hearing that right. 1 quintillion.
Yes.
A billion billions. 10 to the 18th power.
Yes. 1 quintillion unique shapes. Which means your body has the theoretical capacity to mount a perfectly targeted, specific defense against virtually any foreign molecular structure that could ever exist in the universe.
That is just...
It can generate receptors for synthetic lab-created chemicals that haven't even existed in evolutionary history yet.
How do you even conceptualize a system that prepares for things that don't exist?
It's hard to grasp.
It makes me think about it like this. The innate system is like a crew of bouncers at a nightclub.
Mm-hmm.
They are massive. They react instantly, and they just throw anyone out who isn't wearing the dress code or who looks vaguely threatening. It's broad strokes.
Good analogy, yeah.
But the adaptive system, that's like an elite team of bounty hunters.
But not just bounty hunters tracking someone down. Based on the VDJ recombination, they're anticipating the criminals.
Right, so it's like a room full of billions of bounty hunters. And each one of them has pre-forged a pair of highly complex microscopic handcuffs. And every single bounty hunter has a differently shaped pair of handcuffs.
Yes, Cleve.
They're just standing around hoping that one day a criminal walks into the body whose wrists perfectly match their specific handcuffs.
The analogy holds up surprisingly well, and those customized handcuffs, the molecular structures designed to bind to a very specific target, those are the antibodies.
Okay, let's zoom in on that because this leads us right into the B cells. If the adaptive system is the bounty hunter, B cells are the ones actually forging and deploying the handcuffs.
B cells are a core component of the adaptive system, specifically what we call humoral immunity.
Humoral meaning what?
Meaning immunity in the body's fluids. Their primary function is to produce antibodies. Structurally, antibodies are these elegant Y-shaped proteins.
Like the letter Y.
Exactly. The base of the Y is relatively constant, but the two tips of the Y, the antigen binding regions, are where all that crazy VDJ genetic shuffling happened.
Oh, so the tips are the custom handcuffs.
Right. The shape of those tips is completely unique to that specific B cell line. It is designed to fit the specific molecular structure of an invading antigen in a perfect lock-and-key complementarity.
So walk me through the timeline. How does a B cell actually figure out what key to cut? What's the journey of a naive B cell that has just been born and has its unique randomly generated receptor?
Okay, so a naive B cell leaves the bone marrow where it was created and it begins to circulate.
Just floating around.
Floating through the blood, enters the lymph nodes, goes to the spleen, and just continually loops through this lymphatic highway. It sits there wearing its specific unique receptor on its surface, essentially waiting.
Just waiting to bump into the one exact molecule in the universe it was built to recognize.
Exactly. Meanwhile, back at the site of the infection, say, that rusty nail scratch from earlier the innate system is fighting. One of those innate cells, a dendritic cell, engulfs some of the invading bacteria.
Okay.
But the dendritic cell doesn't just digest it and die, it acts as an intelligence courier.
Oh, it travels.
Yes, it preserves key fragments of the bacteria. The antigens places them on its own cell surface, leaves the battlefield, and travels directly to the nearest lymph node.
It's literally carrying a piece of the enemy's uniform from the front lines back to the command center to show the generals.
That is its exact function. It presents the antigen to the billions of circulating B cells. It's a massive biological matching game.
Swiping right until it finds a match.
Basically. And eventually, by sheer probability, a B cell comes along whose randomly generated receptor perfectly locks onto that specific bacterial antigen. They bind.
Jackpot.
Jackpot. And this is a critical piece of molecular logic. Simply binding the antigen is usually not enough to fully activate the B cell to start producing antibodies.
Wait, why not? If it found the perfect match, shouldn't it just immediately start firing the weapons?
Think about the risk. We just established that the VDJ recombination process is completely random. It generates quintillions of shapes. Statistically, it is guaranteed to generate receptors that perfectly match proteins that belong to your own healthy heart or your brain or your joints.
Oh, I see.
Yeah. If a B cell bumped into a piece of your own cartilage bound to it and immediately started firing, it would trigger a catastrophic autoimmune attack. So the system requires a second signal, a fail-safe.
So it's a two-key system, like launching a nuclear submarine.
A very apt comparison. The second key comes from a completely different type of cell, a T helper cell.
Okay, so the T cell has to agree.
Right. For the B cell to launch its attack, a T helper cell must also independently recognize the same antigen and verify that it is indeed a foreign threat. The T helper cell physically docks with the B cell and delivers chemical signals that essentially say, I confirm this is an enemy, you are cleared to engage.
Wow. Only then does it activate.
Only then does the B cell become fully activated.
It's biological two-factor authentication. That is a brilliant quality control mechanism.
It is essential for survival. And once that second signal is received, the B cell undergoes clonal expansion.
Meaning it clones itself.
It begins to divide rapidly, proliferating into an army of identical clones, which then differentiate into two distinct cell types. First, you get plasma cells.
Plasma cells.
These are the heavy industry factories. They drastically expand their internal machinery and just sit there pumping out massive, massive amounts of these specific antibodies into the bloodstream.
How many are we talking?
Up to thousands of antibodies per second, per cell.
Trillions of tiny Y-shaped heat-seeking missiles flooding the blood.
Exactly. And the second type are memory B cells.
Oh, for later.
Right. These cells don't actively secrete antibodies to fight the current infection. Instead, they go dormant. They circulate for years, sometimes for decades, holding on to the precise blueprint of that specific antigen.
So they remember.
If you ever encounter that exact same pathogen again 5 years later, the memory B cells recognize it instantly, bypass a lot of the initial verification steps, and launch a secondary response that is so fast and so overwhelming that the pathogen is eradicated before you even feel a single symptom.
That is amazing. Okay, so the plasma cells are flooding the zone with these Y-shaped proteins. But how do these antibodies actually defeat the pathogens? Do they act like tiny molecular scissors and cut them up?
Antibodies don't destroy things directly, actually.
They don't.
No, they are essentially highly specific molecular tags. They have a few different mechanisms of action. The simplest is neutralization.
Neutralization.
Viruses and bacteria rely on specific surface proteins to bind to our cells and invade them. If antibodies flood the area, they physically bind to all the pathogen's surface proteins, gumming up the works.
It's like putting a physical boot on a car tire. You haven't destroyed the car, but it sure can't drive away.
Right. A neutralized virus cannot enter a host cell, meaning it cannot replicate, rendering it harmless until a macrophage comes along to clean it up.
Okay, what's the next mechanism?
The second mechanism is opsonization.
Opsonization.
This is where the antibodies coat the pathogen, not just to block it, but to paint a target on it.
Like a laser designator.
Yes. The base of the antibody Y acts like a beacon for those innate immune macrophages and neutrophils. It makes the pathogen highly appetizing. The macrophage sees the antibody tail, grabs it, and immediately swallows whatever is attached to the other end.
So it's literally painting a laser target on a rogue agent for the heavy artillery to hit.
Precisely. A third mechanism is complement activation.
What's the complement system?
It's a complex cascade of proteins constantly floating in your blood. When antibodies bind to a pathogen, their tails change shape and trigger these complement proteins to assemble into a literal tube, a microscopic cylinder that punches a hole directly through the pathogen's cell wall.
Wait, it punches a hole in it.
Yes, causing it to burst open, or lyse.
That is aggressive. And are all these antibodies identical, or are there different models for different scenarios? Because I know I've seen things like IgG on my blood test results.
The body deploys different classes of antibodies called isotypes, depending on where the threat is and what kind of response is needed. The main ones are IgM, IgG, IgA, IgE, and IgD.
How do they differ functionally? Let's go through them.
Sure. IgM is massive. It's actually 5 Y shapes joined together, and it's the first responder. It's great at agglutination, which means clumping pathogens together.
Okay, so it bundles them up.
Right. IgG is the most abundant in the bloodstream. It's a single Y shape, it crosses the placenta to protect developing fetuses, and it's the primary driver of long-term memory immunity.
So that's the main one.
Yes. IgA is fascinating because it's heavily secreted across mucosal surfaces. It's found in saliva, tears, breast milk, and the incredibly harsh environment of the gut.
Why is it structured differently?
Its structure allows it to survive digestive enzymes and neutralize pathogens before they even cross the intestinal wall.
Oh, that makes sense.
And IgE is primarily involved in fighting large parasites like worms, but in modern environments, it's notorious for being the primary culprit behind allergic reactions.
Oh, so IgE is why I sneeze around cats.
Exactly. It triggers mast cells to release histamine.
Okay, that clarifies so much. But I have to bring up a detail about B cells that blew my mind when I was reading about it. When they are in the lymph nodes, in these areas called germinal centers, they don't just produce the initial antibodies and call it a day, right? They actively try to engineer them to be better while they were in the middle of fighting the infection.
Yes. You're talking about affinity maturation and somatic hypermutation.
Yes.
It is one of the most remarkable phenomena in all of biology.
If I understand the mechanics of this right, it's like a blacksmith forging a sword, realizing the edge is just slightly dull, and then deliberately introducing chaotic structural changes at lightning speed to try and hone the edge perfectly, all while the army is mid-battle outside.
It is evolution on overdrive, happening in real time inside your lymph nodes.
How does that even work?
Well, as we discussed earlier, normally our cells have massive redundant safety mechanisms to prevent DNA mutation, because random DNA mutation in a normal cell leads to cancer.
Right.
But in the germinal centers, activated B cells do the unthinkable. They deploy a specialized enzyme that deliberately introduces high-frequency point mutations directly into the specific genomic region that codes for the antibody's antigen binding site.
They intentionally mutate their own DNA.
They do. They rapidly mutate, creating thousands of slight variations of the original successful receptor.
Okay, but won't some of those be worse?
Yes. And then they undergo a brutal competitive selection process. The dendritic cells hold out tiny, limited amounts of the antigen. All these newly mutated B cells have to compete to bind to it.
Survival of the fittest.
Exactly. If a mutation made the antibody worse, that B cell fails to bind and is forced to commit cellular suicide apoptosis.
Wow.
But if a mutation resulted in a slightly tighter, better fit with the antigen, that B cell is given a survival signal and allowed to replicate.
So over the course of a 2-week infection, the antibodies don't just increase in number, they get increasingly potent, precise, and deeply targeted.
Exactly. The binding strength increases exponentially. It's a miniature, hyper-accelerated Darwinian selection process contained entirely within a microscopic node in your armpit.
It is stunning. But it brings up a major logistical problem, doesn't it?
What's that?
We have these incredible, highly targeted antibodies hunting down threats in our blood, our lymph, our mucus. But what happens when a virus slips past the antibodies? Antibodies are massive proteins. They can't go inside our cells, right?
They cannot. Antibodies are strictly extracellular weapons.
Right.
They are fantastic for intercepting threats in transit, but viruses are obligate intracellular parasites. To replicate, a virus must breach the membrane of a host cell, hijack the internal ribosomes, and force the cell to print thousands of new viruses.
And once it's inside?
Once a virus is safely inside a host cell, the antibodies are entirely blind to it.
So when the call is coming from inside the house, and the virus is using our own cells as a factory, who do we call?
We call the T cells, specifically the cellular immunity arm of the adaptive immune system.
Okay, break down the T cells. If B cells are the weapons manufacturers, who are the T cells?
Cytotoxic T cells, also known clinically as CD8 plus T cells, are the assassins.
Assassins, I like that.
Their entire biological imperative is to scan the body, identify human host cells that have been compromised by an intracellular pathogen, and eradicate them.
But wait, how can a T cell possibly know what is going on inside another cell? It's outside the membrane. It doesn't have X-ray vision.
This is where we get to what I consider the most elegant surveillance mechanism in biology, the MHC class I system.
MHC class I.
MHC stands for Major Histocompatibility Complex. Essentially, almost every single nucleated cell in your body, meaning any cell with a nucleus, which is basically everything except red blood cells, has a continuous, mandatory self-reporting mechanism.
Self-reporting how? What are they reporting?
Inside every cell, proteins are constantly being built and broken down. A specialized protein complex called the proteasome acts like a molecular wood chipper.
Wood chipper. Okay.
It takes a sample of whatever proteins the cell is currently synthesizing, chops them into tiny little fragments called peptides, binds those peptides to MHC class I molecules, and physically pushes them up through the membrane to be displayed on the outside surface of the cell.
Oh, I love this concept. It's like every single factory worker on a massive assembly line being forced to take a tiny piece of whatever machine they are currently building and stick it in the window facing the street.
Exactly.
That way, the health inspector walking by outside can look at the window and verify, okay, they're building normal human cellular proteins in there. Nothing to see here. Or, wait a minute, that piece in the window is a viral spike protein. They aren't making normal things. They're building a bomb.
That analogy is flawless. The CD8 plus cytotoxic T cells are the health inspectors. They're constantly circulating, moving from tissue to tissue, physically jockeying their T cell receptors with the MHD class I molecules on your cells, and reading the peptides being displayed in the window.
Wow. Just checking windows all day.
If the T cell's uniquely generated receptor recognizes a foreign viral or bacterial peptide on that display, it knows with absolute certainty that the cell has been compromised from within.
But wait, our primary defense mechanism against a viral infection is to systematically murder our own cells.
Yes.
That sounds like a terrible design. If a virus infects my lung tissue, my T cells show up and just start killing my lung tissue. Why is that the best evolutionary solution?
It sounds paradoxical, I know, but think about the alternative. A single infected host cell can produce tens of thousands of new viral particles before it bursts.
Right.
If you don't kill that one factory, those tens of thousands of viruses will infect tens of thousands of neighboring cells. It is ruthless utilitarian math. You sacrifice the individual cell to save the tissue.
Okay, I see the grim logic. So how does the T cell actually execute the hit? Does it just blow the cell up?
No, and the distinction is crucial. If it just blew the cell up, a process called necrosis, the cell membrane would rupture, spilling all those thousands of half-assembled viruses and inflammatory toxic chemicals into the surrounding tissue, spreading the infection.
Which defeats the purpose.
Exactly. Instead, the T cell initiates a highly controlled implosion.
How does it do that?
It locks onto the infected cell tightly. It creates a sealed microscopic gap between them called an immunological synapse. Then it releases specialized cytotoxic granules directly into that gap.
What's in the granules?
These granules contain a protein called perforin. True to its name, perforin molecules insert themselves into the infected cell's membrane and polymerize, forming an actual physical pore, a hole.
It punches a hole in the hull.
Exactly. Then the T cell unleashes enzymes called granzymes through those perforin holes. Once inside, the granzymes don't destroy the cell indiscriminately. They interact with the infected cell's own internal pathways to trigger apoptosis-programmed cell death.
So it forces the cell to commit suicide.
Yes. Apoptosis is a highly organized dismantling. The cell's DNA is chopped up, destroying the viral blueprints, the internal structures collapse, and the entire cell shrinks and packages itself into neat little membrane-bound vesicles.
Oh, like taking out the trash.
Right. There is no explosion, no spillage of viruses, no collateral inflammation. A macrophage then comes along and quietly eats the neatly packaged debris. It is a perfectly clean assassination.
Incredible. Now, earlier you mentioned another type of T cell, the T helper cells, the ones that hold the second key for the B cell activation. Do they kill cells too?
No, CD4 plus T helper cells do not have cytotoxic capabilities, but you could argue they are the most important cells in the entire immune system.
Really?
They are the supreme commanders. They coordinate the entire global response. They do this by recognizing antigens presented not by normal host cells, but by professional antigen-presenting cells like dendritic cells or macrophages, using a different display window called MHC class II.
And how do they coordinate the attack if they don't shoot?
They secrete highly specific chemical messengers called cytokines.
Ah, cytokines again.
Yes. These cytokines tell the B cells to start producing antibodies. They stimulate the cytotoxic T cells to become more aggressive. They summon more macrophages to the area, and they even tell the bone marrow to pump out more white blood cells.
Do they just shout one general command, or are they specialized?
They are highly specialized into different subtypes based on the nature of the threat. For example, if the body is fighting an intracellular virus, a subset called Th1 cells will dominate, releasing cytokines that supercharge the cytotoxic T cells.
Okay, what if it's not a virus?
If the threat is a parasite in the gut, Th2 cells take over, orchestrating the production of IgE antibodies and activating different innate cells. Th17 cells specialize in defending mucosal surfaces against fungal and bacterial infections.
It's like having different generals for the Navy, the Army, and the Air Force.
Exactly. And there's one more critical subtype, regulatory T cells, or TREGs.
What is their command?
Their command is stand down.
Stand down.
Once an infection is successfully cleared, or if the immune system is starting to get dangerously hyperactive and attack harmless things like food proteins or pollen, TREGs secrete suppressive cytokines that calm everything down. They act as the brakes, preventing excessive tissue-damaging inflammation and helping to maintain tolerance.
Okay, this brings up a really crucial, terrifying question.
Uh-oh.
No, seriously. We have these assassins, the cytotoxic T cells, and these massive factories of B cells. Because of that random genetic shuffling, the VDJ recombination we talked about, they can make receptors for literally anything.
Yeah.
So statistically, they must accidentally generate millions of receptors that perfectly lock on to our own healthy heart tissue, our myelin sheaths, our pancreatic cells. How are we not all immediately destroyed by our own internal army? Where is the safety catch?
This is one of the most vital processes in biology, known as central tolerance. The body knows this random generation is inherently dangerous. So, before T cells are allowed to enter the bloodstream and circulate, they're sent to an organ situated just above your heart called the thymus.
The thymus.
You can think of the thymus as an extreme, high-stakes biological boot camp.
High stakes meaning what? Do they have to pass a test?
A literal life-or-death test. Inside the thymus, the newly generated naive T cells are forced to interact with a specialized matrix of cells that present a massive, comprehensive array of self-peptides. The thymus basically displays samples of normal proteins from your brain, your liver, your muscles, your eyes.
It shows them the catalog of us.
Exactly. And the test is simple. If a young T cell's randomly generated receptor binds strongly to any of those self-peptides, it receives a signal to immediately undergo apoptosis. It is executed on the spot.
Wow.
This process is called negative selection or clonal deletion.
So the body actively tests the new recruits, and if any of them show even a hint of a tendency to attack the host, they are destroyed before they ever see the light of day.
Yes. The statistics are staggering. Over 95% of the T cells generated in your bone marrow fail this test and die in the thymus.
95%.
Yes. Only the tiny fraction that prove they will tolerate self are allowed to graduate and enter the peripheral blood to hunt foreign antigens. The body actively purges the T cell repertoire of the cells most likely to cause autoimmunity.
It is astonishing. It's a ruthless system, but it works. And because this entire adaptive system, both the B cells and T cells, is fundamentally built on memory, humanity eventually figured out the greatest biological hack in history.
We did.
We realized we could give the system this long-lasting memory without having to actually suffer through the war and risk dying first.
Yes. We learned to exploit the system's fundamental architecture. Which brings us to the miracle of vaccines.
This is a story of incredible empirical discovery. Let's talk about Edward Jenner in 1796.
A fascinating guy.
This guy is a country doctor in England. He's looking at milkmaids who had caught a mild disease called cowpox from the udders of cows. And he notices that these specific women never seemed to catch smallpox, which was an unbelievably horrific, deadly disease ravaging the global population at the time.
Jenner's observation is the foundational moment of modern immunology. He noticed this cross-protection. The cowpox virus and the smallpox virus were structurally similar enough that surviving one protected you from the other.
Right.
He decided to test it by deliberately inoculating a young boy, James Phipps, with pus scraped from a cowpox sore on a milkmaid's hand.
Which sounds insane by modern ethical standards.
Oh, completely unethical today. He gave the boy cowpox, the boy recovered, and then Jenner repeatedly exposed the boy to actual smallpox material.
Just rub smallpox on him.
Basically. But the boy never got sick. He was completely protected.
What is so wild to me about this history is the timeline. Jenner did this in 1796. This was nearly a century before Louis Pasteur and the establishment of the germ theory of disease.
Exactly.
Jenner didn't know what a virus was. He didn't know bacteria caused disease. He had no concept of T cells, B cells, VJ recombination, or antibodies. He was essentially exploiting complex molecular biology entirely blind.
He was observing a macroscopic phenomenon and exploiting it without understanding the microscopic mechanism. But the principle he established, the deliberate induction of immunological memory through a safe exposure, changed the trajectory of our species. The global eradication of smallpox is arguably the single greatest public health triumph we have ever, or perhaps will ever, achieve.
Let's put some real numbers on that triumph, because it's easy to forget. Smallpox killed an estimated 300 to 500 million people in the 20th century alone.
500 million people.
It had a mortality rate of around 30%. And because of a massive, coordinated global vaccination campaign, it was certified globally eradicated by the World Health Organization in 1980. It just does not exist in the human population anymore.
And the success isn't limited to smallpox. Polio, a disease that paralyzed hundreds of thousands of children annually, has seen its wild transmission eradicated by over 99% globally.
That's huge.
Measles, which is one of the most ridiculously contagious viruses on the planet, used to kill roughly 2.6 million people annually. Today, thanks to widespread vaccination, that number has dropped dramatically, though it threatens to rise whenever vaccination rates dip.
And the technology behind how we deliver this immunological memory has evolved drastically since Jenner was scraping cowpox pus.
Immensely. We progressed systematically. We started with live attenuated vaccines like the MMR or the oral polio vaccine.
How do those work?
You take the actual pathogen and you pass it through animal cells or different temperatures in a lab for generations until it mutates and becomes incredibly weak.
Yeah, it's still alive, just weak.
Right. It can still infect human cells and replicate a tiny bit enough to trigger a robust B and T cell memory response, but it is too weak to cause severe disease in a healthy person.
What's the next step up from that?
Inactivated vaccines. You take the real pathogen and you completely kill it using heat, radiation, or chemicals like formaldehyde. It cannot replicate at all, but its physical structure, the antigens, remains intact for the immune system to recognize.
Like showing the bouncers a dead body.
Exactly. Then came subunit and recombinant vaccines. Scientists realized we don't even need the whole pathogen. We just need to isolate the specific proteins, say, just the spike on the outside of a virus that stimulate the best neutralizing antibodies.
Right, just a piece of it.
We manufacture just those proteins in massive vats of yeast or bacteria, purify them, and inject only the proteins.
Which is like just handing the bouncers the wanted poster, instead of dragging the actual criminal, dead or alive, into the club.
That's a great way to look at it. But the most significant paradigm-shifting advance since subunit vaccines occurred very recently, coming into sharp global focus during the COVID-19 pandemic. And that is the mRNA vaccine revolution.
Katalin Karikó and Drew Weissman won the 2023 Nobel Prize in Physiology or Medicine for the foundational work on this, right?
They did. Their specific work on modifying the building blocks of messenger RNA so that it wouldn't be instantly destroyed by the innate immune system made this entirely new platform possible.
Incredible.
And it fundamentally changes how we approach immunization. Historically, as we just discussed, you had to manufacture the antigen in a giant facility and inject it into a person. mRNA vaccines bypass that entirely. They deliver an instruction manual.
So you aren't delivering the antigen at all. You aren't injecting the spike protein.
No, you are delivering a transient piece of genetic code, the messenger RNA. This RNA contains the exact schematic instructions for building the viral antigen, but getting it into the body is tricky. Naked RNA injected into the blood is instantly shredded by enzymes.
The innate system doing its job, clearing out random foreign RNA.
Exactly. So scientists wrap the mRNA in a microscopic bubble of fat called a lipid nanoparticle. This lipid bubble protects the RNA in the bloodstream and allows it to seamlessly fuse with the membrane of your muscle cells and local dendritic cells in your arm.
And once it's inside the cell,
the cell's own machinery, the ribosomes, read the mRNA instructions and start manufacturing the harmless viral protein, just the spike, not the whole virus.
Right.
The cell then displays the spike on its surface, as well as on those MHC class I molecules we talked about. The immune system sees it, recognizes it as foreign, mounts a full response, creates memory B and T cells, and within a few days, the fragile mRNA degrades completely and is flushed from the body. Your own cells acted as the vaccine manufacturing plant.
It's incredibly elegant. As someone immersed in this field, what stands out to you about this specific shift in technology?
3 profound things. First, safety. Because there are absolutely no live viral components involved and the mRNA cannot integrate into your DNA, it is physically impossible for the vaccine to cause the disease it protects against.
Right.
Second, the unprecedented speed of development.
Yeah, the timeline for the COVID vaccines felt incredibly fast to the public, which caused some anxiety.
But the speed wasn't because corners were cut in safety testing. It was a feature of the technology. Because you just need the genetic sequence of the pathogen, not years of optimizing how to grow a temperamental virus in a lab. The Pfizer-BioNTech and Moderna COVID-19 vaccines were developed, tested in massive phase 3 trials, and authorized in approximately 11 months from when the virus's genome was published on the internet.
11 months compared to what?
That process historically took a decade or more.
11 months compared to 10 years. That is staggering.
And third, it is infinitely adaptable. The platform is essentially plug and play. If a new pandemic virus emerges tomorrow or a significant new variant, you don't have to redesign the manufacturing process.
You just swap the code.
You essentially just type the new genetic sequence into a computer, synthesize the new lines of mRNA code, wrap it in the same lipid nanoparticle, and print a new vaccine. Its manufacturing scalability is transformative, not just for infectious diseases, but we are currently seeing massive trials using customized mRNA vaccines to treat individual patients' cancers.
Okay, we spent a lot of time exploring the brilliance of this system, its memory, its staggering quintillion key precision, and how humanity has harnessed it. But earlier, you mentioned that the central tolerance safety catch, that brutal thymus boot camp where self-attacking T cells are executed, is imperfect.
It is remarkably efficient, but no biological system is 100% perfect. Some slightly self-reactive T cells and B cells always manage to slip through the net and enter circulation.
So they escape boot camp.
Right. And when that safety catch fails and the system turns its weapons inward, the consequences for the individual are devastating.
When the system attacks itself, autoimmunity. Just how big of a problem is this globally?
It is a massive and growing burden. Autoimmune diseases collectively affect approximately 5 to 8% of the global population.
That's a huge number of people.
It has become one of the most significant categories of chronic disease, especially prevalent in developed, industrialized nations. And it disproportionately affects women for reasons we are still working to fully untangle, likely related to hormonal influences on immune signaling.
What does that friendly fire actually look like in the body? Does it attack everything at once?
It generally manifests in two broad categories. First, you have organ-specific autoimmune conditions, where the immune system's crosshairs narrow in on one specific tissue type. The classic example is type 1 diabetes.
That's type 1 diabetes.
In this disease, the cytotoxic T cells mistakenly identified the beta cells in the pancreas as foreign invaders.
The beta cells are the ones that produce insulin, right?
Correct. The T cells systematically hunt down and destroy the beta cells. Once they are gone, the body cannot produce insulin, and the patient loses the ability to regulate blood sugar, requiring lifelong external insulin administration. The body essentially assassinates its own insulin factories.
That's brutal. What are some other organ-specific examples?
Multiple sclerosis is a major one. Here, the immune system attacks the myelin sheaths, which is the fatty protective insulation wrapped around neurons in the brain and spinal cord.
So it's stripping the wires.
Exactly.
Yeah.
As the insulation is destroyed, the electrical nerve signals short circuit or slow down, leading to profound neurological symptoms. Or Hashimoto's thyroiditis, where the immune system attacks the thyroid gland, leading to hypothyroidism.
And what's the alternative to organ-specific?
Systemic autoimmune conditions. This is where the immune system produces antibodies against broad, ubiquitous self-antigens that are found in many different tissues throughout the entire body.
So it's everywhere.
For example, in systemic lupus erythematosus, or lupus, patients often develop antibodies against their own cellular DNA or nuclear proteins. Since every cell has DNA, the immune complexes can deposit in the skin, the joints, the kidneys, the heart, causing widespread systemic inflammation and damage.
Wow.
Rheumatoid arthritis is another systemic example, primarily targeting the lining of the joints but affecting other organs as well.
But why? I keep going back to the thymus. If the body is so incredibly strict about negative selection, how do these self-reactive cells get activated in the first place? They need that two-factor authentication, right?
They do, and breaking tolerance requires a perfect storm of genetic susceptibility and environmental triggers. The mechanisms are complex, but one of the most well-established pathways is called molecular mimicry.
Molecular mimicry.
Yeah.
That sounds like a disguise.
It is a biological coincidence that has terrible consequences. Sometimes a perfectly normal foreign pathogens, say. A random streptococcus bacteria you get infected with happens to have a surface protein whose physical structure is nearly identical to one of your body's own proteins.
Wait, really? Just by random chance?
Yes. There are only so many ways to fold a protein. So you get a strep throat infection. Your immune system mounts a massive, entirely appropriate response. It creates highly targeted antibodies and T cells to destroy the strep bacteria.
Okay, good so far.
The infection clears. But because of that structural similarity, those newly minted weapons cross-react. The antibodies floating in your blood look at the proteins on your heart valves and think, that looks exactly like the strep bacteria we just fought, and they attack your heart. This specific example is called a rheumatic fever.
So the bouncer gets confused because an innocent patron in the club happens to be wearing the exact same jacket as the guy who just started a bar fight.
That is exactly the mechanism. The immune system is doing its job. It's just being fooled by structural similarity. Another major reason for autoimmunity is the breakdown of peripheral tolerance, specifically a failure of those regulatory T cells, the Tregs.
The brakes.
Right. If the Tregs are dysfunctional or depleted, they fail to suppress the immune response after a normal infection is cleared. The system stays hyperactive, the environment remains highly inflammatory, and the threshold for activating those low-level self-reactive cells that escape the thymus drops dangerously low.
But there's an environmental mystery here that I want to dig into. The literature notes that autoimmune conditions, along with allergies, are rising rapidly in industrialized nations. The incidence rates are climbing generation by generation. Genetic changes in human populations take tens of thousands of years to manifest. So if it's happening over decades, it cannot just be genetics.
You're absolutely right. The rapid epidemiological increase heavily implicates our modern environment. We are changing our environment faster than our biology can adapt.
How so?
Researchers are looking at changes in our diet, the impact of chronic psychological stress on immune function, the drastic alteration of our gut microbiomes, and perhaps most fundamentally, our radically reduced exposure to infectious agents.
Which leads to one of the most fascinating counterintuitive ideas out there, the hygiene hypothesis. Is the argument literally that we are too clean for our own good?
The hygiene hypothesis, or the old friends hypothesis as it's sometimes called, proposes exactly that. It suggests that our immune system did not evolve in a sterile vacuum. It was shaped by millions of years of evolution in highly microbial, often parasitic environments.
We were always covered in bugs.
Right. Because of that history, the immune system actually requires continuous low-level microbial stimulation, especially during early childhood development, to calibrate itself correctly.
So it needs target practice. It needs input to set the baseline.
Yes. It needs diverse input to figure out the appropriate balance between launching a full-scale response and maintaining regulatory tolerance. But in modern, industrialized childhoods with sanitized, chlorinated water, pasteurized food, widespread antibiotic use, and drastically less time spent playing in microbially rich dirt, we deprive the developing immune system of that necessary calibration data.
It's like a nation funding a massive, highly trained standing army of 2 trillion soldiers, arming them to the teeth, and then putting them in an environment with absolutely zero wars to fight.
It's a great comparison.
Eventually, they get bored, they get paranoid, their chain of command breaks down, and they just start shooting at civilians in the streets out of sheer hypervigilance.
It's a dark analogy, but immunologically, it captures the essence of the problem perfectly. By stripping away our ancestral infectious burdens, which was a fantastic thing for reducing childhood mortality, obviously we may have inadvertently left this incredibly powerful, aggressive system prone to overreaction. Untangling exactly which environmental microbes are necessary for calibration and how to safely reintroduce that balance is one of the most urgent open questions in modern immunology.
Which brings us to the flip side of this biological coin. If autoimmunity is the tragedy of the immune system mistakenly attacking self, what happens when self actually becomes the mortal enemy and the immune system ignores it? I'm talking about cancer.
Cancer presents the ultimate fundamental challenge to the immune system. When we fight a virus or bacteria, the immune system relies on the fact that the invader is physically and genetically different from us. It has foreign PMPs, it has strange DNA.
Right.
But cancer cells do not come from outside. They come from us. They are our own lung cells, our own skin cells, our own breast tissue that have acquired genetic mutations causing them to replicate uncontrollably and refuse to die.
So because they are derived from our own tissue, they must be covered in all the normal self-antigens.
Exactly. They express the normal self-proteins that our T cells were explicitly trained in the thymus to tolerate and ignore.
So the health inspector T cell walks by the cancer factory, looks in the display window, sees the normal self-proteins and says, "Looks fine to me," even though the factory is expanding uncontrollably and taking over the entire city block.
Historically, that was the assumption that the immune system was completely blind to cancer. However, it's not quite that simple. Because cancer cells are highly mutated and their DNA is unstable, they inevitably start producing malformed or novel proteins that healthy cells don't make.
Oh, mistakes in the factory.
Yes, we call these mutated proteins neoantigens. Because they are structurally novel, they are technically foreign. And we now know that cytotoxic T cells can and often do recognize these neoantigens.
Right, so the immune system does recognize cancer. It knows it's bad. Then why doesn't it just deploy perforin and granzymes and kill it like it kills a virus-infected cell?
Because cancer cells are devious and they evolve rapidly. A tumor isn't just a lump of static cells, it's an actively evolving microenvironment. Cancer cells that are easily killed by T cells die off early. The ones that survive are the ones that have figured out how to actively deploy immune evasion mechanisms.
Evasion mechanisms? Like what?
Remember those immune checkpoints we discussed? The suppressive signals that regulatory T cells use to tell the immune system to calm down and prevent autoimmunity?
Yeah, the biological off switches, the brakes.
Cancer cells frequently mutate to upregulate and express those exact same checkpoint molecules on their own surface molecules with names like PD-L1.
Oh, no.
Yeah. When an assassin T cell comes along, recognizes the mutated neoantigen, docks with the cancer cell, and is about to initiate the kill sequence, the cancer cell engages that checkpoint receptor. It literally reaches out, flips the T cell's off switch, and tells the T cell to shut down and go away.
It's literally a Jedi mind trick. The T cell is standing there with its weapon drawn, ready to fire, and the cancer cell waves its biological hand and says, "These aren't the cells you're looking for."
That is precisely what it is doing at a molecular level. It induces a state in the T cell called exhaustion. And for decades, this was a source of massive frustration in oncology. Researchers knew the immune system should be able to eradicate cancer, but it wouldn't. The immune cells would infiltrate the tumor, but they would just sit there paralyzed by these checkpoint signals.
But wait, if the cancer cell is physically turning off the T cell, aren't we stuck? How do you fight a disease that literally unplugs your primary defense weapon?
That question drove one of the greatest medical breakthroughs of the 21st century, checkpoint inhibitors. James Allison and Tasuku Honjo won the 2018 Nobel Prize for figuring this out.
What do they do?
They realized that if cancer is surviving by using checkpoints to hit the brakes on the T cells, we don't need to attack the cancer directly. We just need to cut the brake lines.
How do you cut a microscopic brake line?
By engineering specific monoclonal antibodies in a lab. They developed antibodies designed to bind tightly to those specific checkpoint receptors on the T cell or the cancer cell, blocking the PD-1 or CTLA-4 interaction.
So they essentially give the T cells molecular earplugs or blinders. The cancer cell tries to do the Jedi mind trick. It tries to hit the off switch, but the T cell's receptor is physically blocked by the drug. It can't hear the command to stand down.
Exactly. The interaction is physically prevented. The T cell can finally clearly see the threat. The brakes are released, and the immune system unleashes its full cytotoxic power against the tumor.
That is amazing.
This approach, checkpoint blockade, has revolutionized oncology. It has produced truly durable, complete responses, meaning long-term, potentially permanent remission in a substantial proportion of patients with highly aggressive, previously untreatable cancers like advanced metastatic melanoma and non-small cell lung cancer.
That is incredible. But it's not a silver bullet for everyone, right?
No, we are seeing around 20 to 30% of patients with certain solid tumors respond beautifully to checkpoint blockade. But for many others, it doesn't work, often because their tumors don't have enough mutations to create recognizable neoantigens, or the tumor microenvironment is too physically dense for T cells to penetrate.
So there's still work to do.
Oh, absolutely. Figuring out how to turn cold tumors hot And identifying the biomarkers to determine exactly who will respond is currently a massive priority in research. But beyond checkpoint inhibitors, scientists have gone even further into what genuinely feels like science fiction. I'm talking about CAR T-cell therapy.
I read this part of the preparation. I had to read it 3 times to make sure I was understanding it correctly. Walk us through CAR T.
CAR T stands for chimeric antigen receptor T-cell therapy. This is a paradigm shift. This is where we don't just take the brakes off the existing immune system, we custom engineer an entirely new synthetic immune system for the patient.
Okay, set the scene for me.
The basic clinical scenario is this. A patient has a devastating blood cancer, say a type of leukemia or lymphoma, a B-cell malignancy that has relapsed and exhausted all conventional treatments like chemotherapy and radiation. The patient is out of options. The doctors hook the patient up to a machine and extract a large sample of their own white blood cells, specifically harvesting their T cells.
Okay, so you physically remove the patient's own assassins from their body.
Right. You take those T cells to a highly specialized, sterile laboratory facility. Using advanced genetic engineering, usually utilizing a harmless, deactivated lentivirus as a delivery vehicle, you insert a completely new strand of DNA into the nucleus of the patient's T cells.
You change their DNA.
Yes. This new DNA forces the T cell to manufacture and display a brand new synthetic receptor on its surface. This is the chimeric receptor. It is part antibody to give it incredible targeting precision and part T cell receptor to trigger the kill sequence. And it has been perfectly designed by scientists to lock onto one specific antigen found on the surface of the patient's cancer cells.
So you pull the soldiers out and you literally rewrite their genetic code to program them to hunt this one specific cancer.
Yes. You turn them into guided missiles. Then you place these newly programmed cells into a bioreactor and grow an army of them. You expand them until you have hundreds of millions, sometimes billions, of these synthetic assassins. And finally, you infuse that living drug back into the patient's bloodstream.
And what happens when they go back in?
They hunt. They circulate through the blood and the bone marrow. They lock onto the cancer cells with their new synthetic receptors, and they eradicate them with ruthless efficiency. In patients with relapsed or refractory B-cell malignancies who previously had no hope, CAR T therapy has produced durable, complete responses in approximately 40 to 50% of cases.
That is a result that would have been completely inconceivable just 15 years ago. Taking a patient's own cells, turning them into a custom-engineered biological weapon, and curing their terminal cancer.
It is the ultimate triumph of translating decades of basic, fundamental immunological research into a clinical, life-saving reality. We are now trying to adapt CAR T to work against solid tumors, which is much more difficult, but the field is advancing rapidly.
Okay, I want to pivot slightly for our final discussion here. Because as we talk about all this assassins, weapons, heavy artillery, intelligence agencies, Jedi mind tricks, guided missiles, it raises a really profound point about how we mentally model and communicate this incredibly complex biology.
It is fascinating. The lexicon of immunology has expanded massively in the public consciousness over the last few years. Terms like antigen, antibody, T-cell, cytokine storm, herd immunity. Well, these were mostly confined to university classrooms and research laboratories. Now they are standard vocabulary in mainstream discourse.
But I want to focus on how we use those words and the specific verbs we attach to them. We've been doing it relentlessly this entire conversation. We talk about the immune system fighting an infection. It defends the body. It attacks the pathogens. It identifies and destroys the invaders. The entire conceptual framework we use to understand our own biology is a militaristic metaphor.
Which brings up a very famous and very important philosophical critique by Susan Sontag. In 1978, she wrote a deeply influential book called Illness as Metaphor. She was writing from her own experience as a cancer patient. She argued quite powerfully that describing illness in these aggressive military terms actually distorts the psychological experience of being sick and places a terrible burden on the patient.
I can see that. If your body is described as a battleground and your immune system is fighting a war against a cancer invader, what does it imply if you don't get better? Does it imply you didn't fight hard enough? Did you surrender? It places this heavy, often destructive moral and emotional burden on the person who is suffering. If you lose the battle, you're somehow complicit in the defeat.
Exactly. Sontag argued that an illness is not a moral failing or a lost battle. It is just a biological process. And the metaphors we use can isolate patients and make them feel responsible for their physiological outcomes.
It's a profound critique. But as an expert who studies the actual mechanisms, how do you reconcile Sontag's very valid psychological critique with the scientific reality of what is happening at the cellular level.
It is a profound contradiction that the medical community wrestles with. Sontag is absolutely right about the emotional weight and the psychological damage that military metaphors can inflict on individuals. We have to be deeply mindful of that in clinical settings and in how we communicate with patients. But on the other hand, as scientists, as researchers, we find it almost impossible to replace those words with non-military alternatives when describing the mechanisms.
Because the analogies are just too functionally accurate.
Precisely. Well, let's just say they map perfectly to the reality. Because at the molecular and evolutionary level, a biological arms race is quite literally what is occurring. Pathogens evolve evasion tactics. The host evolves countermeasures. Cells synthesize and deploy highly toxic chemical weapons. They utilize deceptive signaling. They coordinate multi-pronged systemic assaults to eradicate competing organisms. The functional realities of an offensive and defensive war are genuine. So we are caught in this tension between the stark, brutal reality of the biology and the psychological humanity of the words we use to describe it.
That is such a thoughtful synthesis. It's an evolutionary arms race, but we must never lose sight of the humanity of the person host in the battleground.
Exactly.
Let's briefly recap what has been an absolutely awe-inspiring journey today. We started with the sheer incomprehensible scale of the operation. 37 trillion defended cells. We broke down the rapid, blunt force trauma of the innate system and the staggering, mathematically beautiful precision of the B cells and T cells in the adaptive system. We explored how humanity learned to hack that immunological memory with vaccines, completely altering the course of human history and survival. We looked at the tragic consequences when the system loses its calibration and turns on us in autoimmunity, and the monumental triumph of scientifically reprogramming the system to hunt down cancer.
It's a testament to the power of human scientific inquiry. The fact that we can even begin to understand a system of this complexity, let alone actively manipulate it to save lives, is incredible.
It really is. But I want to leave you, the listener, with a final, slightly provocative thought to mull over on your own. It circles back to the very beginning, when we asked if the immune system was even a single thing, into our discussion of the hygiene hypothesis.
Okay, I'm listening.
Think about this. If our immune system absolutely requires constant microbial stimulation from the outside world to calibrate itself correctly, if it learns the difference between self and other dynamically, constantly updating its definition based on what it encounters in the dirt, the food, and the environment, then perhaps, biologically speaking, we aren't isolated individuals at all. Maybe we aren't walled fortresses fighting off the outside world. Maybe we are walking, breathing ecosystems. And if that's true, then the immune system isn't just a military guarding a strict border. It is a diplomat, constantly negotiating, learning, and managing our incredibly complex relationship with the microscopic world around us. Think about that next time you get a paper cut.